Okay, so so now we are entering chapter 6, and this is our kind of our first step into inference, statistical inference. Okay.
Professor Chen?
Yes. Yes.
Question for quiz next week, is it going to cover chapter 6?
It will not. It will not.
Okay.
So next week's quiz covers up through chapter 5. Chapter 6 will definitely appear on the midterm.
So the quiz would be on chapter 4 and 5?
Yes. Yes. Okay. All right. So chapter 6, it's on confidence intervals. And this is kind of our first step into statistical inference. All right, so you need to, so I guess before we go on, I just want to make sure that we remember what the central limit theorem says. So what does the central limit theorem say? It says the sampling distribution will follow a normal distribution. And what is a sampling distribution? It's the distribution of the sample means. Okay? So we're talking, it's, you know, if we take samples out of the population and we boil that sample down to a single number, that sample mean, what is the distribution of our sample means? What is the distribution of y bar? Okay, and so that's known as the sampling distribution of y bar, and we know that it follows the normal distribution. Okay, so keep that in mind. Okay, so the sampling distribution follows sampling distribution of y bar is a normal distribution. So we know that y bar comes from a normal distribution. Okay, so this is you know, basically the central limit theorem, and then you know there were a few things. It said, you know, the mean is mu and the standard deviation is sigma over the square root of n. So we have the mean and standard deviation defined, and we also said your samples need to be large enough. Okay. All right. So let me tell you what a confidence interval is, or kind of the goal of it. And then we'll talk about this. Okay, so here's the thing. All right, when you do research, you don't get to see the population. Okay, so in the previous problem that we did, this one here, I said the weight of princess bean seed follow the normal distribution. I gave you the properties of the population. I said the population has the mean mu and has the standard deviation or sigma 120, okay? But when you do research, you don't get to see the population, okay? Instead, you only get to see a sample, okay? So when doing research, you only get to see a sample. And we want to make conclusions about the population based on our sample, right? This is kind of the point of statistics. We don't get to see the population. We only get to see the sample. But based on what we see in the sample, what can we say about the population? This is kind of the reason why we bother with this subject of statistics, okay? So let's say you take a sample, size n, okay, and it has the mean y bar. Okay, sample mean is y bar. Okay. Based on this y bar, what can you say about mu? Based on this mean y bar, what can we say about the population mean mu? You know, so if I take a random sample of 40 women and we measure their heights, okay? So we've randomly selected 40 women, we've measured their height, and we got the average height of these 40 women to be 64.8 inches. I don't know, I'm making this up, okay? What can we say about the mean height of all women? Can we say anything? Okay. At this point, we can say, well, it's about going to be probably close to our sample mean, okay? Now, I guess this is a little unfair because you are kind of familiar with the heights of women. But, you know, let's say, you know, we're observing, you know, species XYZ, okay? Species XYZ, we've taken a sample of 40 random things. I don't know how we did that, but somehow we did. We observed, you know, their size, and we got this number. What can we say about the population based on this sample? That's kind of what we're getting at with a confidence interval. And the idea is, with the confidence interval, we want to create a range, okay? So with a confidence interval, we want to create a range of, quote, plausible values of mu, okay? And so essentially, I think it makes sense to say, hey, we're going to put y bar in the middle of our range, okay? And we will go up a certain amount, and then we will go down a certain amount, right? And then we can say, I think mu is between here and here, okay? And then we can say, you know, we think mu is between, you know, here and here, okay? Between the boundaries of this thing. Does that kind of make sense? This concept here? Okay, and so the amount, you know, the amount we're going to go up or down, this is this distance. This is kind of, we're going to call this our margin of error. Okay? So, you know, plus or minus our margin of error is basically what we're saying. Okay, so what should we use? What should we use? Okay, so this is our question that we've got in mind, right? How are we going to make this confidence interval? We're going to say, hey, you know, I got this sample. The mean of my sample is this. I'm thinking the population mean is, it's got to be kind of close to it, so I can say, hey, you know, from here to here, I'm pretty sure that the population mean is between here and here. Okay, so put that on hold, and I'm going to kind of just draw a little analog here. All right, so okay, somebody, so let's say somebody, you see this picture, okay, and you're gonna get to see my artwork skills. This is, it's a dog, okay. All right, and okay, and this dog, it's on a football field, and so we will say he's standing at the 30-yard line, okay? All right, and so but the caption says, so the caption says dog at 30-yard line. Okay, but then it says, where's the owner? Okay, he's invisible, right? So maybe this is on Instagram, so we'll put hashtag he's. Oh, all right, so where's the owner? He's invisible. And we'll also say invisible leash. Okay, so what do we know about this? Okay, so the dog is out with the owner, and there's also an invisible leash. Okay, and the invisible leash is elastic, and so and we also kind of understand the behavior of the dog. So the dog sometimes likes to pull against the leash, but usually doesn't like it because, you know, it hurts his neck. So so we, you know, this is what we know about the dog and the leash. The dog and leash. Okay, so it's elastic, so that, you know, I'm going to say 68% of the time the dog remains within 1 yard of owner. Okay? And then 95% of the time the dog remains within 2 yards of the owner. And what do you think my third thing is going to be? 99.7%? We remember the empirical rule, right? Yeah? 99% of the time? Remains within what? 3 yards of the owner. So, does this kind of look familiar? No? Did I not talk about the empirical rule? I did. Huh? This was from last week with the normal distribution? No? I think? Yeah. So with the empirical rule is if observations come from a normal distribution, 68% of the time they're within 1 standard deviation of the mean, 95% of the time they're within 2 standard deviations of the mean, and 99.7% of they're within 3 standard deviations. So here I'm just talking about a dog though, and the owner, right? Okay. So this is we understand the behavior of the dog, right? So if we see the dog, even if the owner is invisible, we know the owner is nearby the dog, right? And most of the time, the dog's going to be within 1 or 2 yards of the owner, okay? It's possible that the dog is 3 yards away from the owner, or it's possible that the dog's even farther away from the owner, but that's a fairly rare occurrence, okay? So if we see this, all right? If we see this picture of the dog at the 30-yard line, and somebody says, where is the owner? And that the owner's invisible and has an invisible leash, what can we say about the location of the owner? Huh? So we can say something like, I am 95% confident that the owner is located where? Between the 28 and 32 yard lines. Okay? Do we feel comfortable with this statement? Okay. If I wanted to be more confident about the location of the owner, what would I have to do? Would I say, what else can I say? Yeah, I'm 99.7% confident that the owner is between where? Is between 27 and 33. Okay? And so in order for me to be more confident that my interval has gotten the, manages to kind of encapsule where the owner might be, if I want to be more confident, I have to make my interval wider, right? Okay? And I could say, I'm 100% confident that the owner's somewhere on Earth. But that's not very useful, right? Even if I say I'm 99.7% confident that the owner is between 27 and 33, could the owner be at 33.5? Yeah. What does that mean then? It means that this picture was snapped at one of those very rare occurrences where the dog decided to be more than 3 yards away from the owner. Okay? But it is technically still possible. So it is still possible for the owner to be at 33.5. Okay? It's just, we would be surprised if that happened because that happens rarely. But it could happen, right? So the owner could be at 33.5, okay? This would be surprising because the dog does not go, more than 3 yards away from the owner very often. But it is possible. Okay. Okay, and so oftentimes, if we want to be really confident, we have to make our interval really wide, okay? But if someone, asks you, hey, where's the owner? It's not very nice to say, oh, probably just somewhere on that field, okay? He could be anywhere on that field because the leash is elastic. He could be anywhere. That's not very useful, right? So you'd say, oh, well, I'm pretty confident that the owner's between the 28 and 32 yard lines, type of thing, okay? So this is the analog. This is how this story relates to the, or how this scenario relates to the confidence interval, is that we can say the owner is like the population mean mu. Okay? We don't know where the population mean mu is located. Okay? What we do get to see is the location of the dog. And so the location of the dog is like y bar. We do get to see y bar. We don't get to see mu. Okay? However, we know that y bar comes from a normal distribution, from the central limit theorem. So from the central limit theorem, we know that y bar comes from a normal distribution, and the normal distribution says most of the time y bar is within 2 standard deviations of the mean. Okay? 68% of the time, y bar is within 1 standard deviation. 95% of the time, it's within 2. And only rarely is y bar more than 3 standard deviations away from the mean. Okay? So when we see y bar, we can say I'm 95% confident that mu is between here and here. Okay? So let's write this. Okay? So from the central limit there, or wait, let me back up. So, okay, so again, we do not know mu. Okay, we do get to know y bar, okay? And from the central limit theorem, we know that y bar comes from a normal distribution. That has a mean of mu. Okay? And so because we know this, because we know because of this, or because, yeah, because we know this, when we see y bar, we can be confident that mu is close to y bar. And what we mean by close is that, you know, we can be 95% confident that mu is within 2. What's the standard deviation of the sampling distribution? What's that called? 2 standard errors? Okay, right? So I'm going to just write 2 standard errors, or sigma over the square root of n, okay? 2 standard errors of the sample mean y bar. Is this so far okay? Okay. And so we can make something called a 95% confidence interval, okay? Okay. And from here on out, I'm just going to abbreviate confidence interval CI, just because that's what I'm talking about here. Okay. And we can say a 95% confidence interval for mu, for the population mean, is, we're going to go y bar, and we're going to go from minus 2 sigma over the square root of n to y bar plus 2 sigma over the square root of n. Okay. So basically, I'm putting y bar in the middle of my interval, right? And then my margin of error, what's my margin of error then? 2 sigma square root of n, right? So you know, my margin of error And I guess if we want to be more precise, we can use 1.96. Okay. Are we feeling okay with what I've presented here? This idea, yes.
So is margin of error plus or minus the 2?
It's yeah. So you know, when you hear something like so and so is leading in the polls, he got this percent with a margin of error of 3% or something. That means plus or minus 3%. Okay. Okay. There's a problem here, though. Can you guys spot the problem? If I said, make a confidence interval. It's not that they're over. The problem is if I told you, go ahead, you know, here's some data, make a confidence interval. The thing is what's sigma? What does sigma represent? Standard deviation of the population. Okay? Sigma is the standard deviation of the population. Okay? Now keep in mind, we're making a confidence interval for mu, which is the mean of the population. Okay? So I cannot think of any situation, or I'd be very hard-pressed to think of a situation where we don't know the mean of the population, yet somehow we know the standard deviation of the population, right? This probably, there's probably not too many situations where this happens, okay? So in general, okay, we do not know either mu nor sigma, okay? Now, if we did know sigma, then, you know, what I presented on that previous page is fine. You can use that, okay? You know, so our 95% CI, which is y bar plus or minus 2 sigma over the square root of n, cannot be computed. Okay. So what do you think we should do? What should I use for sigma? Okay, so sigma is our population mean, or our population standard deviation. Okay, so if I don't know the standard deviation of the population, is there anything I can do? Huh? A t-value? Okay. Huh? A t z-score? Well, how are we going to get a z-score?
I mean, if it is just 0.5 up to, then we can just get 0.5.
So z-score is y minus mean over sigma, right?
Yeah,
Or
but then since we are looking for 95%, then we can just get that from the table, don't we?
So I think he's saying because it's out of 100, you're looking for 95%, 100 minus 95 is 5%, and divided by the two sides, 2.5 on each side, and then so look for the 25 like percent on the table and then get that z-score. I think that's
well, that'll give us this. That's how we're getting 2. That's how we're getting. If you did that, so when we're doing this, it's technically 1.96 because 1.96 is the thing. You don't have to draw this picture down, okay? 1.96. This is what gives me 0.025 over here, and this gives me 0.025 over here. So that's how I'm getting my 2, okay? But that doesn't solve our problem of what sigma is, okay? So, all right. Well, sigma is the standard deviation of our population. We don't know what that is, okay? So right now, what's our best estimate, or our best guess / estimate of what sigma could be is the standard deviation of our sample. Okay, does that make sense? Right? We have no idea what the standard deviation of the population is, but we do have a sample. And so this is going to have to serve as our best guess for what the standard deviation of our population is. Okay? And so the standard deviation of our sample is S. Okay? So we're going to just plug in S for sigma. Okay? So we will plug in S for sigma. Okay? But that introduces additional uncertainty into our system here, okay? So to compensate for that, I'm going to fudge this number 2. Do you think I should make 2 bigger or smaller to account for the uncertainty? Okay, so remember, you know, if we want to remain 95% confident, about our interval successfully capturing mu, the population mean, and now I'm using a substitute for sigma. I'm using S instead of sigma. What do you think I should do to this number? I should increase it, right? Because I want to remain confident, okay? So we're going to plug S in for sigma, okay? And so to compensate for the additional uncertainty, I will make the factor 2 to something a little bigger. Okay. All right. Now here's another thing. If I take a huge sample, do you think, versus taking a small sample, okay? So imagine I've got different situations. I can take a small sample or I can take a huge sample. Which of those samples is going to give me a better idea of what sigma is? The huge sample, right? The large sample, if I'm using the standard deviation of the large sample, that number should be closer, a better estimate of sigma than the standard deviation from the small sample, right? And so the amount I need to compensate, changing this number 2, I can't just say a one-size-fits-all, okay? I should say, hey, if I'm taking a large sample, I really only need to adjust 2 a tiny bit. On the other hand, if I take a small sample, I should adjust 2 to be something quite larger, okay? Because the larger sample is going to have less uncertainty, but the smaller sample will have more uncertainty. Okay? All right, and so this comes into play. We're going to introduce something called the t-distribution. The t-distribution tells us how much we should adjust and this number 2, this factor of 2, is called the critical value. How much we should adjust our critical value. Okay? So I guess I'll just label this. This is called our critical value. Okay? Tells us how much we should adjust our critical value. Okay? It takes into account our sample size. Okay? In the form of what it calls degrees of freedom. Okay, so we have df equal to our sample size n minus 1. Okay, so degrees of freedom is df, and that is n minus 1. Okay, and so putting this all together, we're going to get y bar plus or minus, and I'm just going to put in the letter t to indicate we're going to take a critical value based on the t distribution, okay? And so sometimes I call this t star. Maybe our textbook says t using, is it alpha or alpha over 2? Basically with n minus 1 degrees of freedom, okay? Multiplied by our standard error, which is going to be s over the square root of n, okay? S, our sample standard deviation. Okay, and so now we will, if we observe a sample, we will have all of these numbers. We'll have our sample mean, we'll have our sample standard deviation, we have the sample size, and then we will use the t distribution to get this number here, okay? So grab your reference tables that I've passed out to you and turn over to table 4, and it says critical values of students' t distribution. The t-distribution has an interesting story of origin. It was developed by a man named Gossett, who worked for Guinness Brewery in Ireland. He was in quality control for the beer brewery, and he was doing statistics. And what was basically happening is he was using basically using the normal distribution for his thing. And they said, hey, and he would be rejecting beers, right? He'd say, hey, this has fallen outside of my tolerance limits, right? He was basically using this thing, okay? And he'd say, hey, this is falling outside of my tolerance limits. I'm rejecting. And then they would have this test, and they'd be like, no, it's actually fine. And he's like, but I'm doing the math, and it says this is falling outside. And he said, well, you must be doing the math wrong. You've got to, start allowing for these slightly extra. You've got to make this. So he manually calculated a whole bunch of standard deviations and tried to understand the distribution of these things, and he developed the t-distribution. It's quite quite impressive. So anyway, this is what your t-table looks like, okay? And so if we're going to go down, and what we do is, so if we want to make a 95% confidence interval, we start at the bottom, okay? And immediately the number right above it is 1.96, okay? And so this is the number that comes from the normal table, and so technically we shouldn't really be using 2. It should actually be 1.96 if we want to be more precise. And that's if we knew the standard deviation sigma, okay? And so we can see if we wanted to be more confident, what happens to the values we use? They get bigger if we want to be more confident, right? And if we're okay with being less confident, we can use smaller values for t here, okay? But let's, 95% is kind of the default value for a confidence interval, but you can make higher, more confident or less confident intervals, okay? And so let's say we have a sample of size 30. Okay, if we have 30 in our sample, and we're going to use that, the standard deviation of our sample of 30, we would have 29 degrees of freedom, n minus 1. And so with a sample of size 30, we wouldn't use 1.96 or 2, we would use the number 2.045. Okay, so we have to fudge our number a little bit and say, hey, if you're using a sample size of 30, then you got 29 degrees of freedom. You got to adjust your t to be bigger, to be 2.045. Okay, your critical value needs to be larger. Okay. On the other hand, if we take smaller and smaller samples, okay, if we take a sample of size 10, I have 9 degrees of freedom, and my critical value now needs to be much larger at 2.262. Okay, so this is like 10% bigger now. Okay, or even more. Okay, so our critical value needs to be 2.262, and we can see, if we take really small samples where we're down to 1 or 2 degrees of freedom, so these are samples of size 2 or 3 or something, then it needs to be quite, our critical value needs to be quite large. Okay, and so our t-distribution tells us what value our critical value should be. Okay, and that's based on the confidence level we want and the degrees of freedom that we have. Okay, our sample size. So let's put this all together, and let's make a confidence interval. Okay, so what we're going to do is we are looking at butterfly wings, okay? So we are doing a study on butterfly wings, on monarch butterfly wings, okay? Oh, I forgot to look up princess beans. Okay, and what we're doing is we've managed to obtain a random sample of 14 butterflies, and we are measuring the size of these butterfly wings, okay? So, you know, we can imagine we would have 14 measurements, okay? There are 14 measurements, but all we need are the sample mean, so the average y bar is equal to 32.814 and our standard deviation S is equal to 2.4757 square centimeters. Okay. So with this, see if you can make a 95% confidence interval. Okay. Well, here, try this out. Okay, so make a 95% CI, and then and over here, make a 90% confidence interval. Or actually, I'm sorry. Looking at the clock, I think I'm going to have to just do this and let you guys catch up. Okay, so what we're going to do is we're going to use our, what do you call this? Equation. So we got y bar plus or minus our critical t times s over the square root of n. Okay, so we have y bar 32.814 plus or minus. Okay, so to look up t, I need the degrees of freedom and my confidence level. How many degrees of freedom do I have? 13 degrees of freedom, right? Degrees of freedom is equal to n minus 1. I have a sample of 14, so I've got 13 degrees of freedom. If I want to be 95% confident, what is the critical t that I'm using? 2.16, right? Okay, so I'm going to use 2.16. Okay, what is my s? 2.4757, and I'm going to divide this by the square root of 14. Okay, so this is just a matter of punching numbers into my calculator. So I'm going to write 2.16 times 2.4757 divided by square root of 14, and I get 1.429. Okay, so I have 32.814 plus or minus 1.429. Okay, so if I subtract off and I add on, I'm going to end up with a low boundary and a high boundary, right? So I can do 32.814 minus 1.429. I get 31.385 centimeters squared, and then I just go back and then I add that instead, and I would get 34.243 centimeters squared. Okay, I'm going to just erase this line for now. Okay, so I'm going to make a statement, and it will be something like, I am 95% confident that the population mean So what's the population, relevant population here? Huh? Now, what is my population? My sample is 14 butterflies, 14 monarch butterflies. So what's the population? What's the relevant population? I'm not asking the population mean. All monarch butterflies, that's what I was going for, okay? So the population is the group that we cannot observe, right? So I'm 95% confident that the population mean of all monarch butterflies ever in the, I guess, currently alive, or I don't know, well, just all monarch butterflies in the world. All right, because I don't know what things were like historically, so we gotta, somehow we have a random sample of 14 monarch butterflies, and this we're hoping is representative of all monarch butterflies. So I'm 95% confident that the population mean of all, or I should mean, I guess, wing size. Okay, because that's what we're measuring, right? We're going for the average wing size of all monarch butterflies is between 31.385 square centimeters and 34.243 square centimeters. Okay. So this is what we're saying about the average wing size of all the butterflies. We're not talking about any individual butterfly. Any individual butterfly, their wings might be huge, or their wings might be tiny. But if we averaged all of the butterflies, if we managed to capture every single monarch butterfly out in the world right now, and we measured all of them, and we took the average of all of those, we're 95% confident that average is between here and here. Okay? Okay, if I want to make a 90% confidence interval, my math would look exactly the same. What is the only thing that changes? Our selection of t. Our selection of t goes from 2.16 to what? 1.771. If I'm willing to be less confident about my interval, I can afford to have something that's more narrow. Okay? And so this would give us two other values, okay? But here I'm now less confident about our statement here, okay? So I'm going to copy this statement onto the next page, and I want to talk about, the types of statements that are okay, whoops, and ones that aren't, okay? So 90% confidence, again, everything's exactly the same. The only thing that changes is this number, okay? The only change. Okay, so here, I'm 95% confident that the population mean wing size of all monarch butterflies is between here and here, okay? I'm going to just write, do not say anything like, I'm 95% confident that the next sample will have an average between, blank and blank. Okay, because I don't feel like writing all these numbers out. Okay, because we're not talking about the next sample. Okay, don't say 95% of butterflies, of monarch butterflies, have wing areas between blank and blank. This is also wrong. Okay, because we're not making statements about. So I'll say, this is wrong, this is wrong, this is correct. Okay, here's a question. can I say, so remember, I just said I'm 95% confident that the population mean wing size of all monarch butterflies is between here and here. Can I say there's a 95% probability that the population mean wing size of all monarch butterflies is between blank and blank? Can I say there's a 95% probability that the population mean wing size is between there and there? So I'll write this down. $31.385. Is this okay? This is also wrong. Okay? And I'll explain why. Because I think this is the one that people have a hard time with. Okay, let's... All right, I've got a quarter here, okay? I'm going to ask you a question. I'm going to flip this coin. What's the probability that it lands heads? So you'd say 0.5, right? Okay, so I'm going to flip this. Okay. All right, I'm going to ask a question again. What is the probability that the coin landed heads? You guys are still saying 0.5? Okay. Well, watch what I'm doing here. I'm going to... Okay. What is the probability that the coin landed heads? Okay, so you guys are like weirded out. Okay, the last two questions, they were trick questions. Okay, before I flipped the coin, it was a totally legitimate question to ask, what is the probability that the coin will land heads? There was uncertainty involved. Probability makes sense when there's uncertainty involved. Once the coin landed, that question of what is the probability was no longer relevant. The coin has landed either heads or it has landed tails. It no longer makes sense to talk about the probability that it will land heads or that it landed heads. It doesn't make sense to talk about probability of things that have happened in history. Okay? You did not know whether it landed heads or tails. You did not know that. Okay? But that doesn't mean that there's uncertainty about how it landed. Okay? So for me to ask you what is the probability that it landed heads, that's a silly question. Okay? It doesn't make sense. There's no probability involved. You can say I am 50% confident that it landed heads because you don't know what it is, but there's no uncertainty about this event. Okay? At least from the frequentist view of probability. Okay? If you talk about Bayesian view of probability, it's different. It's like different philosophies on how probability works. But okay, so anyway, with our classical view of probability, it doesn't make sense to ask about the coin, and it doesn't make sense to talk about the probability that the population mean wing size is this, because the population is all the butterflies out there. The mean wing size of all the butterflies out there is some determined number. There's no uncertainty about it. Okay? There's no uncertainty involved. Like if we were able to measure all the butterflies and get some kind of average there, there's no uncertainty in that number. Okay? We just don't know what that number is. So it doesn't make sense to talk about probability. Okay? The coin landed tails, in case you cared. But this is so it doesn't make sense to talk about probability because there's no uncertainty in the population mean. Okay? I'll write that. mean is a fixed but unknown number. All right, here's another statement. I'm going to ask, is this right or wrong? Okay. I am 95% confident that the sample mean wing size is between blank and blank. Do we think this is right or is this wrong?
Wasn't the sample mean given?
Yeah, we have the sample mean, so this is wrong, okay? The sample mean is known to us, okay? It doesn't make sense to talk about how confident we are about the location of the sample mean. It should be, I'm 100% confident that the sample mean is just this number, okay? Because we know what it is. There's no uncertainty in our sample mean, okay? And it's known to us, so it doesn't make sense to talk about that, okay? All we're saying is that, hey, I observed this sample. Based on the sample, I'm confident that the population mean mu is within, this many standard errors of my sample mean. And so all of these other, things are wrong. Okay, I think that's it for today. Thanks for hanging in there. We'll see you guys next week for the quiz.